Recursion is simply a way to break down a problem into smaller pieces. And sort of technically speaking, it is when a function calls itself, but we'll revisit that definition a bit in a moment. More practically speaking though, what exactly is recursion? Imagine we have these playing cards and we want to count the playing cards. There's an iterative approach where we simply say 1, 2, 3, 4. We have 4 cards. But then there's the recursive approach. Bear with me, this is going to seem like I am greatly overcomplicating the process of counting to 4, but there is a purpose here. So another way to count these cards is to say, well, I know I have 1 card and then I've got all these. We'll call these the rest. So I've got 1 plus the rest. But now, how do I count the rest? How do I know what that is? Well, I know there's 1 card and then again, there's the rest. So I've got this one plus the rest, but how do I count these? Well, I can take 1 card and say I have 1 plus the rest. And now this time, I just have 1 card, there's no rest. Then we can go back up that call stack as we call it. So we can go to the previous call where we said we had 1 plus the rest, and that rest we know is 1, so we have 1 plus 1, that's 2. And then this one we said we had 1 plus the rest, which we know the rest is now 2. So that's 1 plus 2, that's 3. And then we had originally 1 plus the rest, and the rest here we know now is 3. So we have 1 plus 3, which is 4. And that tells us that we have 4 cards. And this is essentially what recursion is. It's solving a very, very small part of the problem and then recursively saying, okay, I'll go solve the rest of it later. And then eventually we go all the way back up to the beginning and we have a completed solution. But okay, now we should look at this more practically speaking with actual code. So here's a factorial function that is iterative. And if you don't remember, the factorial of a number, so for example, factorial of 5 is going to be 5 times 4 times 3 times 2 times 1. So we multiply that number by the n minus 1 until we get to 1. And to do this iteratively, we can start with a result of 1 and we can work our way back up to n. So we start at 2 and we say result times equals our I until we get to n. And you can see factorial of 5 is going to give us 120. And of course, if this was a production function, we'd want to do some error checking to make sure that n is actually a positive integer and all of that. But for now, this function works. But we could also do this recursively. So what would it look like to make this be recursive? Well, the idea of factorial of 5 we know is essentially factorial of 4, which is all of this, times 5. So what if we simply said return n times factorial of n minus 1? So the idea here being n minus 1 is in this case going to be 4. So factorial of n minus 1 is all of this and n is this 5. But now the issue here is this code is never going to end, right? We just keep subtracting 1 from n, but at no point do we say, hey, we're done, we found the solution. So what we can do is add an if check. We can say if n is less than or equal to 1, which is when we're actually going to stop, then we can simply say, in this case, we want to return 1. And now what's going to happen is we call factorial of 5 and n is 5. And we're going to say, is n less than 1? No, it's not. Okay, so the answer is 5 times the answer with 4. Is 4 less than or equal to 1? No, it's not. So the answer to that one is 4 times the answer with 3, and we keep going until n is actually 1, in which case we just return 1. And if we run this, you can see we do still get 120. And really the way I like to think about a recursive function is that it essentially has 3 components to it. So it has this code up here, which we typically call the base case. This is essentially our stopping condition. This tells the function when it should end. And we should always at some point hit the base case, mean get into one of these if checks and return. If you never hit the base case, the function will never finish. And I can show you that. So if I run this, you're going to see maximum call stack size exceeded. We never reached the base case, meaning that this function was going to run forever, and JavaScript just doesn't let us do that, and it gives us this error. But let's put this back and you can see we have 120 again. So that is sort of step 1. I'll say 1 point here. And then we have step 2, and this is our recursive case. So we can say to recursive case, and we're going to say call the function again. But what's important here is that inside of the recursive case, we are subtracting from n. So this is going to look a little bit funny, but what I'm going to do is put this on a new line here and say that this here is actually step 3. And this is going to not just be progress, but progress towards the base case. So essentially, we need to be working towards whatever the parameter is, getting smaller in this case because we're working towards 1. Sometimes that won't be the case. Sometimes we want it to get bigger. Sometimes we want something completely different. But regardless, we need to be making progress towards that base case. And if you have these 3 things, so a base case, so a stopping condition, a recursive case, meaning somewhere where you actually call that function again, and then in that recursive case, if you're making progress towards the base case, then you should have at least a working recursive function. It might not be completely correct, right? Like there's ways I could write this function where it doesn't work. If I did n-2, it is a recursive function. It just doesn't do what it's supposed to do. But at the very least, if we have these 3 steps, we will have a functional recursive function. But now you might have heard a lot of people say that recursion is one of these things. We use it in like coding interviews, but it shouldn't be used all that often. And there is some good reason for this. So let's get rid of this code. And I want to show you a very classic recursive function. So we're going to say function fib of n. So this is the Fibonacci sequence. And the way this works is if n is less than or equal to 1, then what we're going to do is simply return our n. And then what we're going to say is return the Fibonacci sequence of n-1 plus the Fibonacci sequence of n-2. And then if we said down here console.log fib of, let's say 5, run this, you'll see we get 5. And then if we did something like say 10, you'd see we get 55. And the Fibonacci sequence, if you're not familiar with it, by the way, is simply these numbers 0, 1, and then we add those 2 numbers together. So we have 1, then we add the last 2 numbers again. So we have 2, and then we add again the last 2 numbers. So 0 plus 1 is 1, and then 1 plus 1 is 2. And then we say 1 plus 2 is going to be 3. And then 2 plus 3 is going to be 5. 3 plus 5 is going to be 8. 5 plus 8 is 13, and so on and so forth. And this is why the base case is simply to return n, because if n is 0, the answer is 0. And if n is 1, the answer is 1. And again, we could have some error handling for negative numbers if we wanted to, but this is a basic version of the Fibonacci function, and one we see a lot when we're actually teaching about recursion. But this function is not very good. There's an issue with this function, and that comes from the fact that we're using recursion. Because when we use recursion, what we're doing is we're creating sort of a tree of different calls that we're making, and we end up with what we call overlapping subproblems, meaning we do a lot of the same things over and over again. So to show you what this means, let's say we had Fibonacci of 5 again. What is this actually going to do? Well, it's going to make a call to Fibonacci of 4 and Fibonacci of 3. So we're going to have fib 4 and fib 3. Okay, so that seems reasonable. But now we're going to do fib of 4. What is that going to do? It's going to do fib of 3 and fib of 2. And then we also have fib of 3 here. And that's going to do fib of 2 and fib of 1. Okay. And then we'd have another level where we have fib of 3, and this is going to be fib of 2 and fib of 1. And then we have fib of 2. We actually do this twice here, which we'll get into it. That's sort of part of the problem here. But fib of 2 is going to be fib of 1 and fib of 0. And then we do the same thing for this. So here, I'll just copy that. And fib of 1, we know just returns n, so there's no more recursive calls there. And now we have this fib of 2 down here as well. So fib of 2 is again fib of 1 and fib of 0. So these are all of the calls we're going to make. What's the issue here? Well, fib of 0 is called 3 times. Fib of 1 is called 5 times. Fib of 2 is called 3 times, and fib of 3 is called twice. So the issue here is we're doing a lot of the same stuff over and over and over again. And what this creates is an exponential runtime. So I'm not going to get into big O notation here, but if we were, and if you are familiar with it, we would say that this function is big O of 2 raised to the power of n. This is an exponential function. It is going to be very, very slow. And so much so that if I put a big number in here, it might actually take a second. I am running this. This code is running right now. It's working, and we can just wait. I get a sip of water.
1 hour later.
I actually didn't think it would take this long.
1 eternity later.
All right, I waited a few minutes and it was never going to finish. So I've replaced it with fib of 42 to show you that this does work. I just ran it again and this one finishes. It takes like 10 seconds. That's sort of how long I thought the last one would take. And then I realized it was basically just never going to finish the point. This is slow, exponential time complexity because of these overlapping subproblems, meaning we're doing the same thing over and over again. Additionally, we are actually using, so this is the time complexity, we are also using big O of in space. So there's actually space being used up by this, even though we're never creating an array or anything like that. And the problem here is this recursive call. So remember with like the cards, when I had the 4 aces, I said, okay, we do this one and the rest. And we had to keep track of all of this. Like I had to keep all of this in my hand. So until we get all the way back up to the call stack to say, oh, I had 4 cards here, we have to store everything that's happening. So essentially we have what we call the call stack. And this is all of these different stack frames, meaning the information about every single function call all the way up until we actually finish those function calls. So as a result, we end up using a bunch of extra space. So the point here being, this is not a very efficient way to actually do this. So oftentimes we don't want to be using recursion. Now, it is worth noting that this can be optimized. So there's things like dynamic programming, and in some cases, things like tail recursion. I'm going to leave those as topics for another video, but do know there are ways to actually optimize this. But the point here is to show you what exactly recursion is. Now, I do also want to talk a bit about a time when you do want to use recursion, because it's not all like, oh, never use recursion unless you're using these complex methods to optimize it. There are times when recursion actually does make sense. So to give an example of this, I want to talk about something known as recursive backtracking. And this follows a pretty simple pattern. So let's come over here, delete this code. And the pattern here is going to be 1, we want to make some choice. And then step 2 is going to be to recurse. And then step 3 is going to be to undo the choice. And again, we call this recursive backtracking. So as an example of this, what if we wanted to count or find a list of all possible binary strings of some length? So say of length 3, we would have 0, 0, 0, we would have 0, 0, 1, we'd have 0, 1, 0, we'd have 0, 1, 1, we would have 1, 0, 0, 1, 1, 0, and 1, 1, 1. Oh, and also 101. So how could we find this list programmatically? Well, let's try to write a function for it. So let's say function all binary strings of some length n. And let's keep track of a result. So we can say const result is going to be equal to an array. So this is going to be an array of these different strings. And let's keep track of a current path. So let's say const path is going to be equal to also some array. And for this, we are going to use recursive backtracking. So I'm going to implement a function inside of this function. So let's say function, I'll just call this backtrack. And what this function is going to do is essentially generate some of this path for us. And to give an idea of how this is going to work, we're simply going to, at the end of this, be calling backtrack and then returning our result. Okay, so now how can we make sure that inside of backtrack, it is going through all of these paths and updating our result? Well, let's say inside of backtrack, if our path, which is going to be the current sort of string that we have, so if the path.length is equal to n, meaning that we are currently at this point at a length of 3, then we found something to add to the result. So we can say result.push, and we'll push our path. And since we want strings, we will go ahead and just join these like that. But also, this isn't just saving something for us. This is the base case. This is when we got to the end of something we're recursing on. This is when we found a solution. So what we're going to do is simply say return here. And now I mentioned this as a base case, but it is also worth noting that functionally, this is very different from the base cases we saw earlier. First of all, we are building something up. So we are ending when we get to something large rather than ending at something small. So it's sort of the opposite direction of what we saw before. And this is a base case within this recursive backtracking. And we'll see what that means in a second, but it's going to work slightly differently. Okay, so we know if we have this full path, we want to return it, but we've done nothing so far to actually build up that path. All we have so far is essentially this like result here, but we don't have any way to actually build that result up. So the first thing we're going to do when we've called this function, and this hasn't happened yet, is we want to add something to our path. So let's say path.push, and we can just make a choice. Remember, the first thing was just make a choice. So let's say path.push a 0. So we're going to say we start with 0. And then the next step is to recurse. Okay, easy enough. Let's call backtrack. And then after that, we want to undo that choice. Okay, easy enough again. So let's say path.pop. We're going to undo this choice. And then we can do all of this again, but for the other possible choice. So let's copy all of this. And instead of pushing a 0, we are going to push a 1. And now when you look at this code, the first time you look at it, it might be like, okay, I don't really understand what this is doing. And we'll walk through it in a minute. But the crazy part about this code is it's actually done. That's all we have to do. So if we come down here, we could say console.log, all binary strings, and we can pass in an n like 3, run this, and you can see we get those different binary strings. But okay, I think the best way to actually understand how this backtracking works is to walk through an example of this and sort of see it in action. So we start with our path as an empty array and our result as an empty array, and we're going to call backtrack. So in backtrack, we say if the path.length is equal to n, so if it's 3, we're going to do stuff, but it's not. So we skip this. We say, okay, path.push 0. Okay, so our path is now 0. And then we backtrack. What does that mean? It means you call this function again. So if the path.length is 3, we're going to do something here, but it's not. So we continue down here, path.push 0 again, and then we backtrack. So we do the same thing, and we're going to end up pushing another 0. Now, when we call backtrack, we say, is the path length n? It is. This has a length of 3. So we add it to the result. Now it's worth noting this is not removing from the path. It is simply adding to the result, and it is returning, meaning that that last call to backtrack right here, we actually continue. So now we have path.pop. This is the undoing part. So we undo the last choice we just made. And now the path simply has 2 items in it, but after path.pop, we make the other choice. So now we have path.push of 1. So now the path is 0, 0, 1. And again, we call backtrack. And again, if the path length is 3, which it is, then what we need to do is we take this path and we actually store it in the result. So this is now part of our result. Great. But then we also return. And where do we return from? Where we just were, down here. So that means we add, or we do a path.pop. So we continue on. So we call path.pop, which is going to remove this 1. And that is the end of this call that we were in. And this is where it gets a little bit hard to fully visualize in your head where exactly we were. But if you remember, the last thing we did that we haven't returned from was we pushed the second 0, which happened up here, and we called backtrack, and we just returned from that backtrack. So now we need to pop off this 0. So this goes away and we continue. So we push the number 1, and then again, we backtrack. So is the length 3? It's not. Therefore, we push a 0, and then we backtrack. And when we backtrack, is the length equal to 3? It is. So we save this and we return. And what happens when we return? Well, we returned here. So then we undo the last thing. So we undo adding that 0. We continue to add another 1. Again, we backtrack. We end up pushing all 3 of these. So now we have 0, 1, 1, and that is going to cause us to again return. Well, and what is going to happen when we return here? Well, we're going to pop off from the path, and then we're also at the end of the other one. So we actually end up popping again, which I know it's hard to visualize where exactly we are, but this would be the next step. And then we're actually at the end of this initial time that we pushed this 0. So the 0 now goes away. And now we push a 1. So now the first number is a 1, and then we backtrack. And this is going to cause us to do all of this all over again. And we're going to end up with all of these different paths that are going to be the paths we see down here. And you can actually see this in the order that we get them. So 0, 0, 0 is first, followed by 0, 0, 1, 0, 1, 0, 0, 1, 1. And then we would have this 100, 101, 110, and then finally 111 would be the last result. And if you want to really test if you understand recursive backtracking, I think a good sort of test for you would be to work through all of this manually with like a piece of paper and try to draw out that recursive tree and try to figure out what exactly the order is of everything you're going to get. But okay, when is recursion even preferred? From a time and space complexity perspective, honestly, almost never. We've seen that it tends to be less performant. And practically, it's pretty rare that recursion actually shows up in software engineering. It's not a thing that you actually use all that often, but there are going to be some times where it does make sense. Particularly, they tend to be useful when you have problems where some particular data set or data structure sort of lends itself to recursion. So oftentimes this is things like trees and graphs. So for example, we use trees in things like the file system on our computer, and we use graphs for things like social networks. And in both of these, recursion just tends to be an easier way to visualize things, and oftentimes the code is much simpler. But if you're interested in an advanced topic that actually does get used all the time, I would highly recommend you watch this video on promises next.